Good morning, everyone.
Yes, sir.
Okay, and my screen is visible or not?
Visible, sir.
Okay, let's begin the class. Okay. So today so I am at my home. So I am using my mobile network. There might be some problem with network. It will be, since it is slow. So there must be a problem. So please bear with me. Okay. So last time what we have seen is parallel Schwarz inequality. Uh, and using Schwarz inequality, we saw that the norm the norm induced from uh, inner product is actually a norm. Okay, it satisfies the triangle inequality. So let me write the Schwarz inequality here. So say V an inner product space. Okay. And we have two vectors x, y in V, then Schwarz inequality says that the modulus of inner product of xy is always less than equal to norm x number, product of norm of these two vectors. And equality holds if and only if xy is linearly dependent. Okay. So from inner product, we also get the norm of a vector. So how do we define that? Suppose we have a non-zero vector in V, where V is an inner product space, then we define norm X as supremum taken over all mod of X inner product XY, where norm of Y equal to 1. A little hint uh, for this definition of norm X. So consider norm X. Okay, norm X is given by, say, norm X squared. Okay, so this is given by X comma X, correct? So, okay, हाँ, is it?
सर यहाँ पे ये हमारा इनर प्रोडक्ट स्पेस है, ये जो x नॉन जीरो लिया है जिसमें
X नॉन जीरो है, V इनर प्रोडक्ट स्पेस है.
ओके ओके
Okay, we know this thing. Okay, we already know norm X squared equal to inner product of X comma X. So, and using the properties of norm, see here we are taking this is supremum taken over y of modulus of inner product xy, where this y is with norm 1. Okay, so we do a little trick here. We write norm x by, see, this is norm x square. This inner product is norm x square. When I divide this by norm x, it will be norm x, correct? And you know norm x is real number. Okay, and here since x is non-zero, this is always positive, which is same as x 1 by norm x, correct? Using the properties of inner product, I can write this because this quantity is a real number. otherwise it would be a bar of this. You know that x comma alpha y is alpha bar x comma y, correct? So I can write this equality because 1 by norm
सर
x
इसे
is a real number. हाँ
सर इसे सेकंड प्लेस पे क्यों आपने सर नॉर्म एक्स से डिवाइड किया?
ओके, इसीलिए क्योंकि मैं जो डेफिनेशन लिख रहा हूँ ऊपर, सेकंड प्लेस पे क्या है, नॉर्म 1 है.
हाँ सर.
हाँ, तो you know x norm of x by norm x is
1.
1.
हाँ, इसका यूज करूंगा ना मैं,
ओके.
ठीक है, आई बात सुन ले.
बस 1/9x है और फॉर्मूले के हिसाब से मतलब उसको फर्स्ट पे जाना चाहिए ना, क्योंकि उसका बार तो है नहीं.
ठीक है, तो उसका बाद लगा देते, एक मिनट. ओके, लेट्स डू दैट. अब फॉर्मूले के हिसाब से चलते हैं. सो x 1 by norm x r, is it right now?
Yes, sir.
But you know, for a real number r, r bar equal to r. So any real number can be written in this form, r plus I dot 0. When you take bar this, you will get r minus I0. But r,
Yes.
okay, r minus I0 is r. So r bar equal to r. For any real number, it is true. I can omit this bar. Correct?
Yes, sir.
Okay. And now you may proceed. Take this as y. This is actually less than equal to supremum of x comma y, where so this is a particular vector with norm 1. So now here I am replacing this particular vector by y with norm 1. Okay, you know, हाँ, this is model. हाँ, बोलिए.
I have a question. सर
हाँ,
अगर m कोई भी नॉन जीरो नॉन लीनियर स्पेस है और m को
हाँ.
मैं एक स्पेस लेके चल रही हूँ
हम्म.
और मैंने कोई एक सब स्पेस इस तरह से लिखा है कि जिसका नॉर्म 1 है, तो सर इसके बारे में क्या कह सकती हूँ कि ये बना के स्पेस बनेगा या नहीं बनेगा?
आपने एक मिनट, आप बोल रही है कि सब स्पेस का नॉर्म 1 है, तो पहली बात, सब स्पेस के नॉर्म 1 होने से मतलब क्या है? आप इसको सोचिए फिर से, क्या सब स्पेस का नॉर्म 1 हो सकता है?
सर मैं
ओके,
ऐसे एक्स ले रही हूँ जैसे कि जिसमें
सुनिए
नॉर्म
पहली
एक्स
बात.
जो है 1 होगा.
तो वही मैं ओके, रुकिए, पहले क्या ये वेक्टर स्पेस बनेगा?
सर सब स्पेस तो है ही m का.
कैसे सब? एक मिनट, कोई हर एक सब स्पेस एक वेक्टर स्पेस होता है. सबसेट है, बोलिए कि ये सबसेट है. हर एक लीनियर स्पेस एक सब स्पेस होता है. करेक्ट? ओके, आपने ये थोड़ा डाइग्रेशन है इनके क्वेश्चन के लिए. ये क्वेश्चन आप मेरे को इसके बाद पूछती तो बेहतर होता. चलिए ठीक है, आपने एक एम चूज किया एक वेक्टर स्पेस में, एक नॉर्म्ड स्पेस में. आप कह रही हैं कि एम एक सबसेट है जहां पर नॉर्म x इक्वल टू 1 है फॉर ऑल x इन एम. यही बोल रही हैं आप?
यस सर, ये मैं सब स्पेस में ले रही हूँ सर.
ठीक है, एक बड़ा स्पेस है x, उसका सब स्पेस है v, उसका सबसेट है m. ठीक है
सर मैं ऐसे ले रही हूँ कि m कोई भी नॉन जीरो नॉन लीनियर स्पेस है और उसी कोई मैं बना के स्पेस लेके चल रही हूँ. अब मैं उसका सब स्पेस इस तरह से ले रही हूँ कि जिसका नॉर्म लेस देन इक्वल टू 1 है. अब मैं इस सब स्पेस को बना के प्रूफ कर पाऊंगी क्या?
पहला क्वेश्चन, जो आप सबसेट ले रही हैं, क्या वो सब स्पेस है? आपने बोल दिया कि मैं ऐसा सब स्पेस ले रही हूँ, तो इसका मतलब ये नहीं कि वो सब स्पेस है. पहले ये खुद से पूछिए, क्या ये वाकई में सब स्पेस है?
तो सर ये भी प्रूफ करना होगा।
हाँ, क्या वो वाकई में सब स्पेस है? और आंसर है नहीं। क्यों नहीं? देखते हैं क्यों नहीं। Okay, so if it is a subspace, if M is a subspace whose elements are of norm 1, if it is a subspace, okay, then every alpha in K, alpha X will be in M, correct?
Sir.
Then take now norm of alpha X, it will be mod alpha norm X. So whenever mod alpha is greater than 1, it will be greater than 1. So from your definition, alpha X does not belong to M. So M is not a subspace.
सर अगर मैं नॉर्म एक्स को लेस देन 1 तो भी नहीं होगा?
तब भी अब आप इस बारे में खुद सोचिए, ठीक है? हेलो,
हाँ जी सर,
आपको
हाँ जी।
ये आइडिया समझ में आया?
यस सर आ गया।
डेफिनेशन, हाँ, आप तो सबसे पहले उसकी डेफिनेशन को वेरीफाई कीजिए कि क्या वो है या नहीं है, ठीक है? हाँ, ये हो सकता है आपका क्वेश्चन अगर ये होता, इफ वी हैव a Banach space and we have a subspace of this Banach space, whether that subspace is complete or not, means the subspace is Banach or not, then your answer is need not be. Okay. And we have seen such examples. If you remember this, then you know which one is Banach, which one is not Banach. Okay.
Okay sir.
Okay. So back to this norm thing. So now use Schwarz inequality. So you know norm x comma y is less than equal to norm x, norm y, correct? So it will be less than equal to sup of norm x, norm y. But you have norm y equal to 1. This second quantity is 1. So this is norm x. So left side is equal to right side. So use sandwich type theorems. Okay. So norm x equal to supremum of this thing. Okay, so now let's see another thing. Let's ask one more question. We said that every norm, every inner product space gives a norm. It induces a norm, gives or induces a norm. So you may ask, like in metric space, you ask that first you said that every norm induces a metric. Then you ask whether every metric comes from a norm. So here also you can ask the same question, whether every norm comes from an inner product. Okay. So the answer is no again, but we know in which cases every norm in which cases norm comes from an inner product space. So for that, let's see the following parallelogram law. So parallelogram equality. Parallelogram equality. What does it say? What does it say? It says that a norm induced from an inner product on a on an inner product space or on a vector space satisfies the following thing. So norm x plus y square, norm x minus y square equal to 2 of norm x square plus norm y square. Let's see first geometric meaning of this. Why the parallelogram thing is there. So we have two vectors x and wait for 1 minute. We have two vectors. So vector this and say another vector. Okay. Now you know what is the sum of these two. This will be we do that by using parallelogram thing. Okay. So this vector is x plus y. This vector is x plus y. And this vector is x minus y. Sorry. Okay. If this is x, this is y. Correct? So norm of x plus y is norm of this diagonal. Norm of this diagonal. X minus y is norm of second diagonal. So it says the sum of square of diagonals is 2 times the sum of squares of the vectors, and it is a property of parallelogram. So sum of these two diagonals, sum of the square of these two diagonals is equal to sum of squares of all 4 sides. Okay. This you learn in your high school geometry. So let's prove this, and proving this is very easy. So consider x plus y square. You know by definition this is x plus y comma x plus y. Correct?
Yes, sir.
So solve it. Use the properties of inner product. It will be x inner product x plus xy plus yx plus yy. But you know what is inner product x? It is
Norm x square.
norm x square plus xy plus yx plus norm y square. Similarly, norm x minus y square replace y by minus y in this. So you will get norm x square. When you do this, this is minus y plus minus y comma x plus norm y square, correct?
Yes, sir.
But this thing, so you know x comma minus y equal to minus of x comma y. And similarly for minus y comma x. When you add this and this, these two, you will get norm x square plus norm x square, 2 norm x square, xy and x minus y, it will get cancelled. Second term, this third term will also get cancelled. And the last term is norm y square plus norm y square, 2 norm y square. Correct?
Yes, sir.
Okay, so we have proved, so we have proven the parallelogram equality. Okay, so why this equality is important? Why is it important? So if you remember, when we ask the same question for matrix, we have an answer that if a metric is bounded, then it will not come from a norm. Okay. So here also, if any norm does not satisfy and does not satisfy this parallelogram the parallelogram equality, then it does not induce by any inner product. Okay, it is not induced by any inner product. Okay, let's see an example. So what I said is, if a norm does not satisfy parallelogram equality, then it is not induced by an inner product. Let's see an example. Take the same thing that I gave as an example some time ago. What was that? C naught naught and L2. Oh, no, not C naught naught. L2 will be enough. Not L2. L2 is an inner product. LP, because we have seen L2 is an inner product. Let's see LP example. LP where P is not equal to 2. So first see LP. Yeah. Can anyone recall what is the norm in LP?
The norm of XP is equal to summation of mod of
Norm of
X
XP is summation mod of XJP
whole summation 1
1
upon
by
P.
P. Here J runs from 1 to infinity, where X equal to X1, X2 and so on in
Is from
LP,
1.
correct? Okay. So when P equal to 2, this is J equal to 1 to infinity X J square 1 by P. But you know from
1 by 2.
your complex analysis, this is, oh sorry, 1 by 2. Thank you. So this is xj bar. Okay, you know this equality from complex analysis. Okay, from complex number. So, and if you remember, how did we define inner product there? So say if we define xy where x and y are in L2 like this, j equal to 1 to infinity xj yj bar, okay, where for x comma y in L2 define this. So from here, what is x comma x? This is nothing but j equal to 1 to infinity xj bar. xj bar xj square, correct? And when we take square root of this is 1 by 2. And this is what was your 2 norm, okay, in L2. So L2 is a norm. L2 is an inner product space, but for P not equal to 2, LP is not an inner product space. Let's see how. However, LP, P not equal to 2, or in fact not however, whereas LP, P not equal to 2 is not an inner product space. So since it is not an inner product space, therefore it is not a Hilbert space, although it is a Banach space. We have seen that part. So why does not so uh, why does LP not satisfy uh, this parallelogram law? Let's see that. Okay, so I said that whenever a norm does not satisfy the parallelogram equality, it is then we say it is not induced by any inner product. So let's see why. So take two vectors in LP, x equal to 1, 0, x equal to 1, comma 1, comma 0, comma 0, 0, 0. This is in LP, y equal to 1, comma minus 1, 0, 0, 0. Both are in LP, if this is in LP. Then what is norm XP? So for first, this will be summation mod 1 power p is okay, 1 power p is 1 summation this. Okay, why I am writing? So then 0, 0, 0 power 1 by p. Correct? So this is 2 power 1 by p. Similarly, sum of yp is 2 power 1 by p. Okay? But what about norm x plus y? Norm x plus y is, so what is x plus y then? So let's write x plus y here. This is 2, this is 0, 0, 0. Okay? So this will be 2 to the power p, then 1 by p, so it's 2. Okay. And what is x minus y? P. Similarly here, x minus y is 1 minus 1 is 0, minus 1 minus 2, 0, and so on. So this is, so first one is 0, second one is mod of minus 2 to the power p, that is 2 to the power p, then 1 by p equal to 2. Correct? So when you
x minus y पे 0 2
क्या क्या कुछ गड़बड़ है? x minus y कितने हैं देखते हैं. चलो, let's do this calculation. So mod 0 to the power p plus mod minus 2 to the power p plus then again 0 to the power minus 1 by p. So this is 0. Mod of minus 2 is 2.
माइनस 2 नहीं होगा.
क्यों नहीं होगा?
So x minus y
Mod-
कर रहे हैं ना, तो 1 minus minus 1 प्लस हो जाएगा.
Okay, sorry.
तो जहाँ आपने x minus y डिफाइन.
Okay. Thank you. हाँ ठीक है. बट हम उसके मॉड में कोई फर्क नहीं पड़ेगा. Thanks. Okay. So let's do the calculation now. X plus y p square is so 2 square 4, 2 square 4, 8. Okay. And what is this? This is 2 to the power 1 by p plus 2 to the power 1 by p of 2. So this will be Oh, square of that, square of this. Okay, so it's 4 to the power p, 4 to the power p. So 2 into 4 to the power 1 by p. So this is 4 to the power 1 by p. So this is not equal to 8 if p not equal to 2. If p equal to 2, then this will be 8. Okay? Correct? If you calculate this, if p equal to 2, then this is 4 into 4 half, which is 4 into 2 equal to 8. So this means this left hand side equal to right hand side. See here, where is this? At this place.
LM equality. If P is
Huh?
so if P is equal to 2, it satisfies inequality.
Yeah,
Equality.
equality. It satisfies equal. It satisfies parallelogram law. Okay. So I always say inequality. So so it's equality actually. So that's why parallelogram law is better name for this. Okay. So it satisfies parallelogram law when p equal to 2. Otherwise, it is it does not satisfy parallelogram law. Okay, so this means L2 is not an inner product space. Okay, there is one more example coming from the space of all continuous functions. Okay, on AB with this norm, with infinity norm, sup norm. So please try it yourself. So I have given a hint in your notes. Do it your own. Okay. So here, what we have seen that every inner product space induces a norm, and we have also seen that there are some norms which are not induced by any inner product, but if we can ask, if we are given a norm which is induced by an inner product, can we rediscover inner product, the original inner product? Okay, we are given only the norm, which, and it is true that this norm is induced by an inner product, and we do not know anything about inner product. The only thing we know is norm. So question is whether we can rediscover the original inner product from the given norm. Okay, so the answer is yes, we can do that, and we do that by polarization identity. Polarization identity. What is that? If so I'll write it in two ways. So when our inner product space is a real inner product space, means if the field, underlying field is real number, then we define, see, we want inner product using norm. So see, I'll use only norm in the right side. So this will be norm x plus y square minus norm x minus y square. So when k equal to real number, so the field R, k is the field R, then we do this thing, and it is easy to see. How? Let's go to the parallelogram law. So x plus y square, so norm of x plus y square is this thing. Norm of x minus y square was this thing. When you subtract norm of x minus y square from x plus y square, so now this part will get cancelled, okay? Norm x square, norm y square, they will get cancelled. So the only thing that remains is norm xy plus, sorry, inner product xy plus inner product yx. There it will be plus inner product xy plus inner product yx. Correct? When k is r, when the field is r, you know xy equal to yx. Otherwise, it is bar of this. Okay? Any doubt? Hello?
Yes, sir.
Is, is, is everything okay?
Yes, sir.
So you can do this your own.
Yes, sir. ट्राई कर सकते हैं.
ओके सर.
इसमें ट्राई करना है, ये तो हो गया. देखिए एक्स
हो
प्लस वाई
जाएगा
स्क्वायर
सर.
कितना था? नॉर्म एक्स स्क्वायर था, एक्स वाई था, ये आपने पहले देखा है.
नॉर्म वाई स्क्वायर.
नॉर्म एक्स स्क्वायर, so this is minus y. अब इनको सब्ट्रैक्ट करोगे तो ये वाला पार्ट कितना आएगा देखते हैं. जो भी आता है सब्ट्रैक्ट कर रहे हैं हम, ठीक है?
हो जाएगा.
So ये get cancel, this two get cancel, we will get xy, yx and plus xy plus yx. Correct? But since we are in the field of real numbers, so you in this case xy equal to yx. If we are in complex number, it is bar of this. Correct?
Yes, sir.
So these are four, total four.
4 times.
So it 4 will go this side. Correct? Okay, if k is complex number, if k is the field of complex number, in this case y will be 1 by 4 of, so there are two parts, the real part and imaginary part. So real part will be the same, which is here. So it is x plus y square minus x minus y square. This is the real part. Now the imaginary part, plus I x plus iy square minus x minus iy square. Please do it your own. It's simple calculation, okay? Okay. So far what we have seen that every norm that satisfy a parallelogram equality is induced by an inner product, and we can rediscover that inner product using only norm, and that thing can be done by polarization identity. Okay. Okay. Now let's come to something called subspaces. Same thing that, so I'll recall it fast because you already know what a linear subspace is. So suppose we have an inner product space. So X an inner product space, okay, and y be a non-empty subset of X, y is called a subspace of X. Number one is a subspace. If y is a linear subspace, means treating X as a vector space, y is subspace of X, linear subspace of X, number one thing. And second thing, the inner product that induces from X is same in Y. Okay, this means X comma Y. When we restrict it to Y, we get the same thing, same inner product. Okay, so if these two conditions hold, then we say Y is a subspace of the inner product space X. So what is then we talked about closed subspaces in when we were doing normed spaces. So you know if you remember, how did we define closed subspaces in normed spaces? The same thing holds here. See, every inner product space is a normed space, correct? Every inner product space is a normed space. So therefore, Y is closed subspace of X if it is closed as a normed space, normed subspace. Okay. Consider Y as a normed subspace of X. If Y is closed in X, then Y is called closed subspace of the inner product space X. Similarly, for completeness, so see, closeness, completeness, they come from metric space thing. Okay. If you remember this, while defining closeness, completeness, we use metric property of norm. So same thing will occur here. So since every inner product space is a normed space and normed space is a metric space, therefore whatever we have done there in normed space, we can do it in inner product spaces as well. Okay, so let's okay, so for, if you remember, for complete normed space, we gave a name to complete normed spaces. We call them Banach space. Correct? Here, every complete inner product space is a Hilbert space. Okay, so if you remember in normed space theory, so subspaces of a Banach space, subspace of a Banach space need not be a Banach space, correct? You saw some examples where subspace was not complete. So the same thing will happen here. Okay. So do you remember any normed space which was complete and a subspace of that normed space which was not complete? Do you remember any such example? Today I gave one. हाँ
का सबस्पेस C0 0 लें तो सर वो इनकम्प्लीट होता है।
हाँ लेकिन एलपी में तो एलपी में यहाँ पर एलपी अगर P2 नहीं होगा तो वो इनर प्रोडक्ट स्पेस नहीं होगा,
तो
है ना? तो यहाँ पर हमको L2 लेना पड़ेगा उसकी जगह, ठीक है? So L2 is an inner product space which is complete, means L2 is a Hilbert space, but its subspace C naught naught is not complete. So it's not, so why is so? Because C naught naught bar is L2 and you know C naught naught not equal to L2. So for closeness, closure would be the same thing. Okay. Okay, then now let's come to, okay, we have enough time to give a notion. So if you remember, when we were beginning this unit 3, I told you that normed spaces do not give a concept, a geometric concept that is called angle between two vectors. But we may define, in fact, we define angles via inner product space. Okay. So when we talk about angle, we talk about perpendicular thing, perpendicular angle. Okay. So perpendicular vectors. So another name for these vectors is orthogonal vectors. Okay. So let's define what is orthogonal vectors. Definition. Let X be an inner product space a vector X in X. So we have two vectors, say X comma Y are two vectors in X. We say X is orthogonal to Y if, so if you remember your 11th, 12th class, in intermediate class, you study vector calculus there, vector. So when are two vectors perpendicular to each other? What is the condition for that?
डॉट प्रोडक्ट जीरो होना चाहिए था
डॉट प्रोडक्ट जीरो होना चाहिए था। और
यस सर
अगर आप याद कर सकते हैं तो हमने ये क्लास डॉट प्रोडक्ट से शुरू करी थी। मीन्स आज की क्लास नहीं, ये यूनिट जो है डॉट प्रोडक्ट से शुरू की थी। हमने बोला था कि हम कुछ एक ऐसी चीज डिफाइन करने जा रहे हैं जो डॉट प्रोडक्ट का जनरलाइजेशन है। ओके, सो एक्स इज ऑर्थोगोनल एंड वो जो डॉट प्रोडक्ट का जनरलाइजेशन है वो क्या है? इनर प्रोडक्ट। ओके, जो अभी हमने डिफाइन किया इनर प्रोडक्ट। इफ दिस इज जीरो इट्स द डॉट प्रोडक्ट इज, अगर हम केवल जो वेक्टर आपने वहां पढ़ा है वहां पर वो डॉट प्रोडक्ट था, यहाँ पर ये इनर प्रोडक्ट है। ओके, so two vectors are orthogonal to each other if their inner product is 0, and in this case we write x is perpendicular to y, and we write, okay, so suppose we are given a set A, so we are given a subset of A, and we have a vector x in X. So what does it mean by x perpendicular to A? This means
X is perpendicular to each element of A.
X is perpendicular to A for all A. Okay, let me write the exact thing. This means the inner product is 0 for all A in A. And say we have two subsets of A and B are two subsets of X, then what does it mean by A perpendicular to B? This means take inner product A of AB where A comes from A and B comes from B. Okay. So if you see xy equal to 0, this means yx is 0. Correct? This is because xy equal to inner product yx bar, but this is 0. 0, 0 bar is 0. Okay. So from this observation, what we see x when x perpendicular y is same as y perpendicular to x. Okay. And one more thing, this is equal to inner product of x and 0 is
0, sir.
0, and this is true for all x in x. Okay. So if x is non-zero, then x comma x is norm x square, and you know when x is non-zero, this is always positive. So this means 0 is the only vector in x which is orthogonal to itself. So if you are given something that a vector which is orthogonal to itself, you will answer that it will be 0. Okay. So when we talk about perpendicular things, so see we are in R2, say we are in R2. So we have two perpendicular vectors. Say this is one vector, this is another vector. Okay. अच्छा नहीं बना. So this is another vector. So there is a relation. So this is x, this is y. X is perpendicular to y. What can you say about x plus y norm of this? And how do you define in first place? How do you define x plus y? So for that, what you do this thing.
diagonal
Okay, ऐसे नहीं. Diagonal of this. इसको ऊपर बढ़ाएंगे, इसको इधर ले जाएंगे, मान लेते हैं कि ये परपेंडिकुलर. ठीक है, मान लेते हैं ये रेक्टेंगल है, लग नहीं रहा लेकिन मान लेते हैं. Then this will be x plus y. Okay. Now if you remember, so this will be y then, and this is x plus y. And do you know what is the relation between, this is a right angle triangle, and you know Pythagoras theorem. So what does Pythagoras theorem say? It says this square equal to norm x square plus norm y square. Okay. Can you prove this? Yes, you can, because it's now very easy. Because this norm x plus y square is, how do you write norm x plus y square in inner product space?
Plus y, x plus
Huh?
x plus
X
y,
plus y comma x plus y. Now do
norm
this.
x
So
square
norm x square,
plus
बोलिए.
inner product of x comma y
and
हाँ,
inner product
plus inner product of y comma x plus norm y.
norm y. But x is perpendicular to y. This means
zero
this is
हो जाएगा ना.
0, this is 0. So you are left with norm x square plus norm y square, which is this thing. So this means you have just proven the Pythagoras theorem. Okay. So I'll at the end I will give you a definition and I will leave you with this definition. Think about it. So this is very geometric. You okay? Do you see it's very geometric? Are you getting it? आ रहा है ये समझ में?
Yes, sir.
Okay. So now we define orthogonal complement of a set for any set E of X. The set we say E perp. Okay. We call E perp. PRP or sometimes E perp. So this is called E perp. And it is the orthogonal complement of E. Means all those vectors in X which are perpendicular to E. Means which are the inner product is 0 for all U in E. Okay. It's called the orthogonal complement of E. Okay. So a simple example, what is perp? What would be 0 perp? Orthogonal complement of 0 is
0
जीरो का किसी भी
0 तो ठीक नहीं
x हो जाए
हाँ
कि सबके साथ
see
ही ये 0
x comma 0 for all x in X. This means 0 perp is X. What is X perp?
x पर x x किसी साथ 0 नहीं होगा
तो
0
इसको ऐसे लिखना चाहिए मुझे हाँ x perp is 0. Okay. Okay, I'll stop here. Please drop your attendance. We will meet on Monday. Any question? Doubt कोई? Hello?
सर
सर
कोई
रिकॉर्डिंग
क्वेश्चन है?
सर
रिकॉर्डिंग मैं शेयर करूंगा अगर मेरा क्योंकि मैं घर पे हूं और मेरा नेटवर्क बहुत स्लो है अगर वो सही से डाउनलोड हो जाता है और फिर उसको अपलोड भी करना होता है मुझे पहले डाउनलोड करता हूं फिर उसे दूसरी जगह अपलोड करता हूं जिसका लिंक आप लोगों को भेजता हूं मैं अगर मैं नहीं कर पाया तो 15th के बाद जब भी यूनिवर्सिटी खुलेगी तो मैं तब कर दूंगा ठीक है अदरवाइज मैं कोशिश करूंगा कि कोई लिंक बना के आप लोगों को भेजूं
ओके सर थैंक यू सर
ओके ओके बाय